This is the practice exam for Chapter 5. This is number 4. A horizontal spring of force constant 300 newtons per meter is compressed at a distance of 0.31 meters. A block of mass 15 kilograms is then placed at the end of this spring, and the spring is released. The block slides along a frictionless table and then up a frictionless slope. It says see diagram. So here's the diagram. Yeah, kind of sketchy. But it's good enough. Find the speed of the block just after it leaves the spring, and then find the maximum height the block reaches on the slope. Okay, so first off, this is frictionless. Go full screen. Okay, so I don't have to worry about work done by outside forces like friction. Basically, what I'm looking at here is conservation of energy problem. So initial energy is going to equal final energy. Well, initially, the spring is compressed and everything's just staying still, and I'm going to say that right here, that this height is a height of 0. I'm going to call that height of 0. So the only energy that I start with is spring potential energy. Okay? Then, right after the block leaves the spring is no longer compressed, so I'm not going to have any spring potential energy, but I'm still at height of 0, so I'm not going to have any gravitational potential energy, but I will have kinetic because it will be moving by that point. Okay, so that's going to be 1/2 spring constant compression distance squared equals 1/2 mass times velocity squared. Alrighty, well, I've got a half on both sides, so I'm just going to go ahead and get rid of them. Okay. I am solving for the speed just after it leaves. So that's going to be v squared. So I'm going to solve for v squared. So that's divide by m on both sides. I end up with spring constant times compression squared over m. That's going to equal v squared, so I'm going to square root it to get v. Okay, that gives me spring constant was 300. Okay, 300 newtons per meter. I don't have room for that though. It was compressed 0.31 meters. 0.31 squared. Don't forget to square it. And then the mass was 15 kilograms. Again, sorry about the lack of units. Okay, if I put, sorry, that bothers me. If I put that all together, what I get is that the velocity just after leaving the spring is 1.39 meters per second. 1.39 meters per second. Okay. For those of you that prefer to start with the big long equation and go from there, that would have looked like, oh boy, it would have looked like kinetic initial plus gravitational potential initial plus spring potential initial plus work net equals all those things as finals. Ooh, let's see if I can squish it in here. And then there are no outside forces, so this is gone. It starts at rest, so this is gone. It starts and ends on a height of 0, so these are both gone. And the spring ends up non-compressed, so this would be gone. So I just end up with this equals this, which is where I was. Okay. All right. So that was A. Then for B, they ask how high does it go? Now there's two ways to do this. I could choose that where the block leaves the spring is my initial, or I could use the spring being compressed as the initial. I will find a little bit more accuracy and less rounding errors if I start all the way from the beginning again. Okay, so this time I'm starting with spring potential energy. This is still gone, this is still gone, this is still gone. But at this point, now I'm going to ask how high does it go? So at the very, very, very top height, it will stop, so this will go away, but it will be at some height, so this will still be here. However, the spring will not be compressed, so this is still gone. So same equation, initial energy still equals final energies because there's still no friction. It's just that this time it's going to be the spring energy turning into gravitational potential energy. Okay, so I'm going to have 1 half spring constant compression squared equals mgh, where h is as high as it goes. Okay, and I'm solving for h. So let's see, I'm going to divide by m and g, so that's going to give me kx squared over 2mg equals h. No square roots this time. Okay, so that's my 300 newtons per meter times my compression squared over 2 times the mass was 15, and g is 9.8. And that gives me that the maximum height is, I get 0.09806 blah 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 blah. Okay, I only had 2 sig figs, and it rounds out nicely for that anyway, so I'm going to put 0.098. And since everything was in standard units, this should be in standard units too, meters. Okay, let's talk about points. Well, first off, let's give a point for the right answer on each part. Okay. Let's see, if you have some sort of statement of the conservation of energy, either in this form or straight up into this form, that's a point. And you get that for each part, so same thing over here. It might be that you did this with the big long equation and you cross things out, leaving this stuff behind. That would work too. Okay, for getting the correct equation for the spring energy, that's a point. If that happened to be in conjunction with, like it was up here, if you didn't do USI, you just went right into this, that would be okay. You'd get a point for this and a point for having it all arranged properly. You get a point for having the proper equation for kinetic energy, and you get a point for having the proper equation for gravitational potential energy. I'm not going to give you 2 points for the spring, even though it happens twice. Okay, then how about a point for putting things in the correct places? I only have, 3 points left, so let's do 1 for k, 1 for x, and 1 for m. And that's, I think that's right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yep, that's it.